Hi guys, hope you all enjoyed the last sessions. Before going to the next session, we just discussed what we learned till now. Let us recap the sessions. What we learned electric charge, properties of charges, methods of charging a particle, Coulomb's law and equation. What is the equation of Coulomb's law? By Coulomb's law, the electrostatic force F is equal to 1 by 4 pi epsilon 0 Q1 Q2 by R squared, where Q1 and Q2 are the charges and R is the distance between the charges. Epsilon 0 is the permittivity of free space. And we discussed about the significance of Coulomb's law. We compare electrostatic force and gravitational force, and we discuss about superposition principle, that is the electrostatic force when multiple charges, more than two charges are there. So these are topics that we discussed till now. So let's start our today's session. Before starting the main topics, let us discuss about some important topics or important terms that we are going to use throughout this chapter. When we talk about the continuous charge distribution, we consider three cases. One is a linear conductor, that is a copper wire or iron wire. So it is a linear wire. So in that case, that material also have charge. Okay, so in that case, we have to consider the linear charge density, and it is denoted by the symbol lambda. Charge per unit length is called linear charge density, and it is by equation we write it as lambda is equal to charge by length, and its SI unit is centimeter per meter. And if we consider a surface, for example, the surface of a table or a plain metal sheet, or when we consider all the surface, we are considering surface charge density, or we can say charge per unit area, and it is denoted by the letter sigma, small letter sigma, and its SI unit is centimeter per meter square. And next thing is volume charge density. So if you are considering a cubical block or a cylindrical block, so charge is contained in the entire volume. So in that case, we consider volume charge density. Charge per unit volume is known as volume charge density. It is denoted by the letter rho, and rho is equal to charge per volume, and its SI unit is centimeter per meter cube. So these are the three important terms that we are going to discuss when we thought about continuous charge distribution. First one is linear charge density, second one is surface charge density, and third one is volume charge density. Okay, so please keep these terms in mind when we go through the chapter. Now we are starting with today's topic, important topic, electric field. So when we talk about electric field, there is something called magnetic field that you learn in 10th, that is introduction, and in the chapter 4 and 5 we are going to discuss detailed about the magnetic field. So whatever you are learning in this chapter, similar things you are going to learn in chapter 4 also. The change is in this chapter it is electric field, and the chapter 4 it is magnetic field. So if you study or understand this chapter very well, that fourth chapter is also easy. So when we talk about electric field is a region where a charge can exert a force. Suppose if there is a charge we kept on the top of this table, and if some other charge come to near to that, so there is a space or the area that this charge can attract or repel the new charge. So after that particular area, this charge cannot exert any force. So the area that a charge can exert a force is called electric field, and we can define electric field E is equal to F by Q, where F is the electrostatic force and Q is the charge. The magnitude of electric field is the force per unit charge, and its direction is that of force. That is, force is a vector quantity, so electric field is also a vector quantity, and direction of the electric field is same as the direction of force, because charge is a scalar, it doesn't have any direction. And the unit of electric field is Newton per coulomb, or we write it as Nc raised to -1. Now we are coming to the details of electric field. So when we talk about electric field, this year we are only discussing about a point charge. So when you talk about electric field due to a point charge, the magnitude of electric field due to an isolated positive charge is plus Q. At a point P, distance r away in a medium of permittivity epsilon can be calculated by imagining a very small charge plus Q placed at P. By Coulomb's law, the force F on Q is F is equal to 1 by 4 pi epsilon 0 Q0 by r squared. So Q0 is the point charge and Q is the new charge coming to the vicinity of the electric field or the discharge or the electric new charge coming to the electric field. So by Coulomb's law, F is equal to 1 by 4 pi epsilon 0. Here medium is there, so instead of epsilon 0 we use epsilon Q0 by r squared. And in the previous session we learned that E is equal to F by Q. So when we divide the above equation with Q, what we got? It is 1 by 4 pi epsilon Q0 by r squared. So the equation for electric field due to a point charge is 1 by 4 pi epsilon Q0 by r squared. If there is no medium, we use 1 by 4 pi epsilon 0 Q by r squared, or we can write 9 to 10 raised to 9 Q0 by r squared. That is the equation for electric field due to a point charge. So when you talk about electric field, we have to discuss about the electric field lines also. So we know that there are two charges, positive and negative, and we know that there are some force of attraction or repulsion between them also. So how this exerted? So we represent that force and visualized by electric field lines. An electric field can be represented and visualized by electric field lines. And if you want the direction of a particular point of a electric field line, just draw a tangent at that point, and the tangent give the direction of the electric field at that point. And always it starts from positive and ends at negative. The field lines due to positive charge is represented by a straight lines originating from the charge. You can see right side the figure. It is originating from the charge. And in case of negative charge, it is terminating or it comes towards the charge. That these are some properties, and we are moving forward. We are discussing other properties also. And if there are two charges, positive and negative, you can see on the right side of the figure, it starts from positive and ends at negative. And it close to the charge, the density is higher, and moving away from the charge, the density is little bit less, or it is not a straight line, it is a curved path. And if we take two plain charged conductors, then it is not a curved one, it is a straight line. You can see from the right side. The lines of force containing more than one charge distribution. From each charge we can draw the lines isotropically. The lines may not be straight as one moves away from the charge. You can see in the figures. So it is from moving away from the charges, the lines are not straight because it is due to the repulsion of the lines of force. So near the charge, it is due to the strong attractive force of the charge, it is becoming closer. But when it's moved far away from the charge, due to the repulsion between the lines of forces, it just start moving away, and the gap between the lines of force increasing. The number of lines originating or terminating on a charge is proportional to the magnitude of the charge. That is, if the charge is higher, the number of lines is higher, and if the charge is less, the number of lines is less. Now we are moving to the next topic, electric flux. So if the lines of force through a surface, then the surface is said to have flux linked with it. That is, if some electric lines or electric field lines or lines of force is passing through a surface, then we can say that surface have some flux. So it is given by d phi is equal to E dot ds. E dot ds. E and S are vector and all are in same line, but due to this some technical error it is shown in different layers. So all are in same line. E dot ds. So E and S are vectors, that is why the arrow is on the top. When ds is the area vector of a small area element, that is, in physics when we discuss about a particular thing, if we first consider a small portion and then later we integrate. That is what we are usually follow in physics. Like that, if a person is going on a bike with very high speed, we say that, oh, that person is going at very high speed. But sometimes he may come slower or faster than previous case, and all later case also he may drive faster. But we are considering that small portion and considering that small interval or small portion, we are assessing the nature. So like that, here also we are taking a small area. The area vector of a closed surface is always in the direction of outward drawing normal. That is, if we consider table as the surface and the area vector is perpendicular to the surface of the table. That is, if we are pointing a pen on the table, so it is perpendicular to the surface. So the area vector is always normal to the surface. And the total flux linked with the body phi is given as surface integral E dot ds. So when we integrate d phi, we got phi. So the integration we will discuss in the 7th chapter of mathematics this year. So that the time we will discuss detail. Here we just understand integration means summing up or collecting all the small pieces. Simply we can say like that. So the SI unit of electric flux is Newton meter square per coulomb. Now let us discuss about the electric dipole. So similar to electric dipole, there is magnetic dipole also that we will discuss in the chapter 4. So by definition, electric dipole we can define like that. Two equal and opposite charges, let us take the charges Q plus Q and minus Q, separated by a small distance 2a. So why we take 2a? Because in coming sessions for the derivations, if we take 2a, that is better to derive some derivations. That's why we take 2a. So we can take any measure 2a, r, x, d. Okay, so in different textbooks it may differ, but 2a is more convenient for coming proofs. That is why I take 2a here. Small distance 2a is called electric dipole. So two equal and opposite charges separated by a small distance is called electric dipole. So when we talk about electric dipole, we have to discuss about the electric dipole moment also. So electric dipole moment is a vector quantity whose magnitude is equal to the product of the magnitude of either charges and the distance between them. That is, we denote the dipole moment as p, small p. It's a vector, so there's a arrow at the top. P is equal to 2aq. 2a is the distance and q is the charge. So P is equal to 2ak. That is the equation for dipole moment. By convention, the direction of dipole moment is from negative to positive. So direction of dipole moment is from negative to positive, and as a unit of dipole moment is coulomb meter.
Please like and subscribe our channel for more videos.